Alright, time for another draftphysics.com video presentation. So it's a response video to the RSD Academy guy, again, some effort to communicate with other people, making arguments about how things work. And there should be some ability. I mean, it seems this problem on the internet where everybody's a seller, okay, and they're just selling for their audience, and that's it, and there's no haggling between any of the people, in terms of buying, okay, and in terms of refining ideas. So it's just a bunch of cults standing on their little podiums, and nobody's arguing between them the philosophy. They're just preaching a philosophy, and that's I think not good. But in a sense, this video highlights a part of it, which is he's making a counter argument, a haggle against Veritasium. But again, there won't be any formal acceptance or rejection of any kind of ideas, and so the whole thing just kind of doesn't work, because I think people have to haggle in a more direct way rather than indirect. But anyway, so I'm going to talk about electricity. I'll just point out the air track, it's raining, but yes, so far so good. Working out the springs and the different things, and so we'll see. Coming soon, probably. Anyway, the theory seems to work anyway. Alright, so I'll play some of this, and then I guess what I will do is make the counter argument. So he's talking here about the idea of a lumped model and defending it. And all you're really saying is how specific does a model have to be? And clearly I think it's a big problem in that some models are so distant from the facts, like the bent fabric thing for gravity. That's a lump that's way too lumpy, because it's not three-dimensional. It really doesn't fit. It really doesn't explain. So he has drawn, what you can get this idea of electrons go in and electrons push out the other side, and he's talking about the speed of sound because he's using glass beads as an example. And it's not a terrible model, but I think it falls far short of recognizing what electrons are. So I guess I'll do that part first, and then I'll come back to playing it. So there's lots of elements here to haggle over, and like I said, some of it I think can logically be understood, so there should be no argument in a sense, because there's certain facts that we do know that sort of say, well, you have to change that model. So the first argument I would make is that this is a conductor, and what are we really saying is happening when you're going to create electricity flowing through the wire. Now my argument would be is if I'm going to use little round things to say, okay, that's the concept, we're just going to push these little round things, then the first thing I'd say is if you want to get the model closer to the reality, is to recognize that electrons are obviously repulsing to each other. So let's just say electrons were the only thing in the universe. We can, we'll just say for the sake of argument that the protons aren't playing any significant role except being what happens when you don't have electrons. So I guess I would argue is that the electricity is really just a phenomenon of how dense the electrons are. So if you have too few electrons, you have a relative positive, and if you have more electrons, you have the higher negative. So the more electrons you have, the more negative it is. The less electrons, the more positive it is. But the fact is you're really just saying there's a certain number of electrons, and we can have any artificial ground. So we could say 50 electrons is the ground, 100 electrons is negative, and 25 electrons would be positive. Okay. Yes, it's backwards because, Benjamin Franklin made a bad guess. So I'd say to model electrons, right, what you would model them as is not glass things pushing on each other. You'd model them because they squish into each other. They're elastic. Okay, they're really elastic. So you think of them as North Pole magnets. So if we just establish that, yes, that would be a better model, that we're really pushing North Pole magnets into North Pole magnets, okay? And we have a certain amount of space in here. So you have a bunch of North Pole magnets inside the wire, all right? And they've all shared their pressure, okay? They're done jiggling, they've settled, and they're all going to be equal distant theoretically. So if you did actually put a bunch of North Pole magnets in a confined space, they will equidistance themselves from each other. All right, so we'll have an equal amount of pressure between all the electrons theoretically. You know, all of this pressure would be the same. And so if I'm going to do a lump model, that would be a better metaphor. So a lump model just means metaphor, I suppose, analogy, and you're really trying to get it as close as you can to the actuality. The better the lump model is the model that is exactly what the actual thing does. And you're just using these approximations because you can't know the actual thing. So you're trying to approximate the actual thing. So the first approximation, I'd argue, is that you have to understand that this is an elastic relationship between the electrons. They can move away from each other, they move into each other, they have pressure between them that's variable. And that pressure is essentially going to be voltage. Okay, high pressure, high voltage, low pressure, low voltage. That's the wrong way to say it, right? Because if it's really low pressure, it's going to be a high negative voltage. All right, anyway, so the idea is you're basically just saying that in theory, what the wire is doing is pushing another magnet into the confined space. All right, but now I'm going to argue the space isn't truly confined. The space is being confined because of the protons. So the protons are playing the role. It's not like the electrons can't escape the wire because there's a wall they hit. They don't hit the wall of the wire. What they hit is the wall of getting too far from the proton. The proton is attracting them, and so they're getting pulled into each other by the protons. So the protons are scattered in between, and they're going to keep all the electrons from trying to leave. So you have to think of it as a, what do you call that, a plasma of sorts, where it's independent because the protons are creating the requirement that it be in a confined space. So the protons are saying, I want you to be as close to each other as possible. The electrons are saying, I want to be as far away from each other as possible. So you have the balance of those two forces. So when you're introducing another electron, so you push one electron into that, what it's going to do is that pressure is going to be shared. Okay, you're now creating extra pressure because you've got a confined space. You're increasing the density of electrons. Okay, the charge density, you're increasing it in this space confined by the pulling action of the protons. And so what I'm going to argue is happening is, yes, that expansion, that increase in the pressure, if you thought of it as a box of BBs, all right, and you put a piece of matter in the BBs, you could sort of understand that the piece of matter will fill up a piece of the space, and by filling that space up, it's going to make these BBs more energetic. They're actually going to have more kinetic, they're going to have more momentum because you've filled a space they can't occupy anymore. You've changed how much volume they're in. The volume of space they're free to move in is now smaller, so they're going to hit things more often. Same rule here. You've introduced another electron. You're increasing the energy inside the space because you're occupying more space that the magnetic force isn't allowed to occupy. So if I fill this with another electron, then this reflection would happen sooner, and this reflection, and this, So if you just think of these as the electrons like ping pong paddles, lump model, and the stuff between them, the force that's causing them to hate each other are balls bouncing off of them. You can increase the force by adding more balls, or you can increase the force by pushing the electrons, the paddles, closer to each other, because there'll be more impacts. All right, so the idea is you should start shoving this electron in. You're increasing the pressure, and one of the pressures you're increasing is pressure out, okay? Because the walls are artificial. This wall is artificial. It doesn't really exist. This wall is artificial. It doesn't really exist. The thing holding it together is the force of the protons, and that didn't change. You didn't add any protons. So the force of the protons can't stop, it doesn't have enough force to stop the fact that it will also, the pressure will move this way. So the pressure will move in this direction, and it'll move in this direction and this direction. And so for an instant, okay, your surface is going to go from a certain size, and it's going to get a little bit bigger. And what's the consequence of that increase in the size of the volume that your electrons are taking up is this little difference here. So you've changed this size, and that little difference, okay, is essentially what's going to be called the electromagnetic field that's going to radiate off the wire. So when I first put the charge in, I increase the pressure expands down the wire because the electrons are all connected to each other, but also pushes up this way a little too. So electrons move off the surface, but they can't move very far without getting too far away from the protons, right? So again, the argument is the protons are what's holding it together, and it's not going to allow it to fly apart. All right. So this little tiny pulse happens. And just understand that if I don't let this pressure decrease, that is, I don't let it go back to the size that it was, then I'm just did that one pulse. All I did was move the surface from here to here. So I moved the surface from one place, running out of space, and I just moved it up a little. And I did that relatively fast. And so that is what the rest of the universe is hitting that surface. And now what have I done by moving this surface fast is that I've created all the reflections that would have happened all in this space are now going to happen as a clump. Okay, all those reflections are going to be much closer to each other. So they would have been expanded like, one here, one here, one here. They would have been filling a wider amount of space, and now they're just going to be condensed into a smaller amount of space. So you're taking something that would be rather random, okay, in terms of the clumpiness, and you're making it more. You're putting it more in a clump, and there happens to just be more of it for that millisecond, and that's the pulse that goes across the field to the other conductor. So the other conductor, when this expands, is going to get hit with a little burst of radiation just during the period of time of the expansion. So as it expands, it creates a little extra thickness, density of magnetic pulse. The magnetic pulse hits this and does the same thing. It pushes on these electrons and creates the same phenomenon of pressure in this wire. In this wire. So this wire now has pressurized electrons that want to go this way, and they want to go that way too. Okay, on the positive side. On the negative side of the wire. So, as a lumped model, I'm saying this is a better model, and it also, by putting the force in there, you can understand that drift velocity is just nonsense. Because drift velocity is considering the whole journey being one electron traveling the whole distance rather than the force between the electrons traveling the distance. So the argument would be is that the force between the electrons, the pressure, these little arrows of pressure, all right, no matter how you understand them to be created, I'm arguing they're all just reflections. Okay, just like the Earth, the electrons are in space and they're reflecting the universe. Okay, they're at equilibrium. The energy that comes in comes back out again. And, with that tiny bit of gravitational difference, but whatever, won't get into that part. So the pressure between the electrons is really, this is the pressure is moving at the speed of light. The electron might move really much slower, but the point is the journey, right? Can you see this journey line? A little bit. The whole journey, okay, of these electrons moving, the point is the electrons are really far apart, so only a tiny part of the journey is the electron moving. The rest of the journey, 99.9999998% of the journey, is going to take place between the magnetic fields. So you could imagine if you had really strong neodymium magnets, they could be 10 inches apart, okay, and still push each other. You push one and the other one moves. So a huge amount of the transfer of the movement is happening at the speed of light through the force, and only a tiny percentage is the movement of the actual magnet. So that's why electricity moves at almost the speed of light, is because only a tiny percentage of the pressure change is happening at less than the speed of light. Most of it's happening at the speed of light because the magnets communicate at the speed of light. Their pushing force already exists. Okay, it's already at the other object, so to speak, and the increase, that is, when you increase the pressure, it'll increase at the speed of light. So most of the space is between the electrons, and so most of the movement will be conveyed, most of the information, if you want to call it that, will be conveyed at the speed of light, and only a tiny percentage of it will happen at the speed of the electron. So drift velocity, I've already explained, is a nonsense, because that's just taking an average of what every single electron is doing at any one moment, and at every, and only a tiny percentage of the atoms in the material, depending on how much voltage you put in and amperage, are actually being involved in this process. So it's stupid to compare all the horses that are in their stable and then, average it to the horses going around the track and saying the horses going around the track are only going, 5 feet an hour, when no, you don't average them with the horses in their stable. Okay, you only average the ones that are actually moving, and then you average them based on how much distance how fast the actual message to move is sent, and the message is being sent at the speed of light. Alright, so you can sort of get the idea that that's why this message, okay, this pulse, only lasts as long as this pulse lasts. So as soon as this expands, if I don't allow it to contract, that is, I don't reduce the pressure, I can't send another signal here. Okay, it's not like it's sending constant, saying I'm under pressure, I'm going to send more stuff, I'm going to send more stuff. It only sends stuff when it's moving, okay, getting fatter and getting thinner. So then it's the only time it's sending, a 0 and then a plus, and then a 0, less than, I guess I could say it that way. Okay, less density, more density, less density, more density, based on how big the wire's getting. So I have to keep changing it if I wish to change it in here and cause current to move. So I can only send the pulse, and that's it, and then it's gone. It's a transient. It only lasts for a second, and the pressure moves through the wire, and that's the end of the pressure. So it gets a tiny bit fat, and then the whole thing just loses all of its pressure because it shares with all the other electrons and dilutes the whole thing, and so the pressure's gone. So it only lasts for that little instant. Now if I allow it to go the opposite direction, that is, I allow the pressure to reverse, you can see how alternating current then keeps the wire keeps changing, and so it keeps sending plus minus plus minus plus minus plus minus plus minus. Then it can keep pumping electricity, alternating current. It can create an alternating current, but I can't DC induce a current because all I get is that first enlargement, and because I never let this go back down, it never can send any more signal than that one little impulse, and that's it. And that's what you get on your needle. You get that little tiny inductive voltage that disappears because it dissipates, and then the current shows up from the wire. So I really don't want to have to erase this. So an interesting change to the experiment would be just to put the light bulb in a different position. So we have the idea of the battery here, all right, and we have the light bulb here, all right, and we're doing this induction thing. So as soon as we allow this wire to get fat and this wire to get thin, all right, and we're sending a signal here that says thin here and it says fat here. So we sent less force hitting this wire and there's more force hitting this wire. Therefore, this one gets higher pressure, this one gets lower pressure. And we get that little instantaneous burn. So what if we move the light bulb over here? Okay, so if the further off that center we move that light bulb, now we have to wait for the speed of light, because now we have to wait for that pulse to get to the light bulb. So that will delay the amount of time it takes for the light bulb to do that little blip of, I got the inductive current. Okay, I felt the pressure from your wire getting bigger, and boom, pressure, no pressure, pressure, and then that's it just stays there, and the other side equalizes to it, and that's it. You can only increase, it's only while it's moving it's brighter. Right there, that instant, it's brighter, but when I stop here, I'm back to normal. I'm getting the normal amount of reflections. I'm not getting more reflections because I'm bigger. So I don't know how to say that exactly. It's only the moving part, okay, is where you're collecting extra photons. You can't collect extra photons by just moving from here to here, unless there was more, like you were getting closer to a light. You're not getting closer to a light. All right, this is probably more than enough subjects in here. I mean, I could get into the capacitor analogy or lumped model, but I don't think there'd be much. I don't think there's much hope in anybody having the conversation. So I don't know for what purpose there is to even talk about anything on the internet. But anyway, let's see. So we'll go to the video.
The marbles carrying the energy, it's an acoustic wave, but the marbles facilitate that.
Right, so the first argument I would make is that acoustic wave, you're being very two-dimensional, and not, it's like the bent fabric analogy for gravity. It's missing a huge component in the sense that the analogy shouldn't be to marbles, it really should be to magnets that are repelling each other, because that's the real circumstance. Electrons repel each other, and it's a very elastic repulsion. That is, whatever pressure they increase by getting closer, it's real pressure, and there's every likelihood they're going to expand at some point as soon as that pressure is relieved.
So I would really like to see Derek clear that up, because as soon as he's...
Yes, well, he didn't clear anything up. He just chose to use different words to say exactly the same thing. So his initial video was titled something like, "Energy doesn't flow in wires." And he's still trying to say the same thing, which is just wrong. All right? I mean, induction is a side effect. It isn't what the wires are doing, so to speak. Okay? The electricity has its own energy and its own kinetic energy, and it's just a symptom of its energy that it now reflects to the rest of the universe differently, because it expands because it has more energy. Okay, you're increasing the density of the electrons, you're giving them a higher profile while they're increasing. While the pressure increases or decreases, you're changing what reflects off the object. So the field effect is just a symptom.
Says this model's bad, people are going to look at my videos and comment, "You idiot, don't you know that model's wrong?"
Yeah, the point is it's not complete, and how distant is it from the actual truth, and how many essential elements is it missing? And I would just argue that, look, you could just fix the model. I mean, you could make it better, in my opinion, all right, by just concluding that yes, what's really moving through the wire is the pressure between the electrons, because that's going the speed of light. That's how you get the signal from one end of the wire to the other end of the wire at almost the speed of light. Is the fact is that most of the communication between the electrons is taking place between their negative repulsive fields. The fields around the electrons are conveying the pressure.
Model is correct. It's an acoustic wave carrying the energy, not the mass of the marbles.
Right. So it's, it's wrong to say it's an acoustic wave. That really doesn't mean anything, in the sense that what it is atoms moving. That's what an acoustic wave is atoms physically moving. So you're physically pushing on the atoms. And what makes atoms move isn't that atoms hit each other, it's that their electron pressure hits each other. Their electrons get closer to each other between the two atoms. That pressure is real and it wishes to push.
Another thing I need to clear up starts at about 5 minutes and 50 seconds into the video.
As you go along the wire from the negative end of the battery to the positive end, there is a gradient of charge built up on its surface.
Alright, so there's no gradient once you've charged it. So that's like saying there would be a gradient of charge on a capacitor surface when you've established you've charged the capacitor, which isn't, there's no gradient. The entire wire will be whatever it's connected to. So if it's connected to the positive end of a battery, that end of the, and you're going to switch the negative end, the fact is that the entire length of the wire is now positive, and the whatever the distance is to the switch is the negative side. You're increasing the surface area of the poles of the battery, but it's a tiny increase in the sense it's not a capacitor. It's not plate against plate. There's not a huge amount of surface area. The difference between a capacitor and induction, in a sense, is that capacitors essentially create an infinite plane. So if I have a big sheet of something, you can sort of understand that if I'm sending signal out of each little spot here, if these were all LEDs, you could understand, and this side was all LED, all receivers of the energy, diodes, light, electricity creating diodes, photoelectric diodes. And I put the plates closer and closer, you can sort of understand that the stuff here in the middle, now light going this way and going this way and going all the different ways, is still hitting the surface. So I'm breaking the inverse square law. So the closer and closer I bring the two plates, the closer I bring the surfaces, it's almost as if it's a literal infinite plane, and that nothing can escape. No matter how I cone the light from any one location, unless it goes at the 90-degree angle, it can't escape. It has to hit the other side. It has to hit a photodiode. So I've guaranteed, by having a large surface area, I'm guaranteeing a reduction in the inverse square law, so I'm collecting more and more, a higher and higher percentage of the signal. So it's like having radio antennas that were like a capacitor. In the sense, you're just going to guarantee that the energy has to get to the other antenna. They can't miss it, okay? Because you're essentially creating an infinite plane. And a wire doesn't do that. Obviously, a wire is just a little thing in space. It's radiating in all directions, and so only a tiny bit of the energy will go from one wire to another wire. Because it's not an infinite plane. The energy is going in all kinds of directions, spiraling out of that antenna, and you're missing most of it. You're not collecting hardly any of it. And the way like transformers work is they create coils that, again, create infinite planes, essentially. They guarantee that the wire will be hit by the energy.
Starting with an excess of electrons through to roughly no charge in the middle, as we'll see, the steepest charge gradient is actually across the load, to a deficiency of electrons,
So the only thing the load is doing is decreasing the pressure, right? So that's how we're getting energy out of the load, is that it's consuming the pressure. So you're just going not from negative to positive, you're really going from negative to less negative, less pressure. But it's not truly positive. It only becomes positive because as you reduce the number of electrons, you increase the density of the protons. So, so in that sense it does become positive, but it's only becoming positive because you reduce the density of the electrons.
Exposed positive cores of atoms on the surface of the positive end of the wire.
Okay, what I need to clear up about this is what he says is true when there is current in the wire. And
So I would argue that the gradient still isn't true. And the gradient is so tiny, it just has to do with the resistance of the wire. And again, in Veritasium's video, he said they were perfect conductors. So there would be no point in having this argument about the resistance of the wire because he said they're superconducting wires. So I'm not trying to do a gotcha. I'm just saying this is not the, this is really not the subject. And the fact is there is a voltage, whether or not there's a current or not, it doesn't matter because the voltage essentially is just charge. And you've charged the capacitor, so to speak. As soon as it's connected to the circuit, it's charging, and then it's charged.
I think this is going to confuse the beginner if I don't straighten this out. So we have our...
A beginner is not going to stand a chance, right? Because, frankly, you have to understand that there are electrons and protons and this and that. Yeah, well, anyway.
Battery and our wire. Here's the light bulb.
So in my example, what if you move this light bulb over here, or you moved it over here, and so now you're changing this part of the connection. So, what if the field has to get all the way to here before there can be an inductive current,
Remove this light bulb, there will be no voltage gradient across here. To get that voltage gradient, you need two things.
So again, the voltage gradient that Veritasium we're talking about wasn't one created by the resistance of the wire, because he had already stipulated that the wire in this case was going to be a superconductor. So that wouldn't make any sense.
You must have current and you must have resistance. Maybe even an infinite resistance, but you must have some resistance. Without current and resistance, you get no voltage gradient. I explained this many times in my classes.
Right, the resistance is just the load. The resistance is just the thing that's going to consume it. So you're just saying that if I put some kind of garbage, I put junky pieces in the wire, impurities, then when the pressure hits those impurities, instead of it being elastic, it'll be stuck inside that impurity, or it'll go in the wrong direction. Okay, it won't play along with, it's a disruption to how the pressure migrates through the wire.
So right now, let's say this is a 10-volt battery. If I put a voltmeter across here, I'm going to read 10 volts. If I put the voltmeter across here, I'm going to read 10 volts.
Right, so this is with an open circuit. So all it's doing is charging to the same pressure as the battery. The battery has a high density at one end, a low density of electrons at the other end. The high density end says, ooh, I have a place to go now, so I'm going to go into the wire and I'll increase the pressure of the wire to the same pressure I have. So the wire equalizes to the pressure that the battery can produce, and it doesn't matter that there is any resistance in the wire because, yes, when it's initially charging, there'll be a resistance, but as soon as it's charged as a wire, that is, as soon as it's equalized to the battery contact, then it's going to be exactly the same because resistance doesn't matter anymore because I don't need to keep flowing. I don't need to keep, I'm already there. I don't need to drive there, so I don't have to hit any lumps, or I don't have to hit any speed bumps. I don't have to hit anything that's going to get in my way because I'm already there. I've already charged the capacitor, so to speak.
If I put the voltmeter across here, I'm going to read 10 volts. There is no voltage gradient without current. Now, you could argue, well, there's a leakage current around there, which means there's going to be a slight gradient. You're not going to measure it, okay? So near as makes no difference. There is no voltage gradient if there is no current. But as soon as I put that light bulb in there and get current, now...
So I think this is a small point, and I think, he's really kind of pushing, just because now he's going to use numbers like, well, yeah, 99.999999% of the voltage will be there. Well, even that can be hard to read. If I make wires exactly this small, I'm not going to be able to tell the resistive difference between this point in the circuit and that point in the circuit because there isn't enough wire to create enough resistance for me to measure it. So theoretically, that resistance doesn't exist because I can't measure it.
I have current flowing through the circuit. I'm showing conventional current as I usually do, and as most people in the industry do. So let's see what happens.
So obviously I would argue that that convention is a really poor lump model, right? Because why would anybody draw the current going in the opposite direction of the voltage? We know the energy really is the pressure, the high pressure. I don't see anything to be gained by saying that somehow the change is moving in one direction, in terms of the number of atoms being involved, and that the way the atoms are being involved is moving in the opposite direction. It doesn't make much sense.
Now, well, I'm now going to get that voltage gradient that he talks about down this wire. So I get a little bit away from that battery. I'm going to read something less than 10 volts. How about 9.999 volts? Further down here, I'm going to have...
Right, and if I make these wires short enough, you're not going to read, it's not going to be 0.99, it's going to be 0.9999999. It's a tiny resistance.
Even a lower voltage. How about 9.998 volts, or whatever it is? I'd have to do some calculations knowing the resistance of the wire and the actual current in the light bulb. Too many things to know here. But I would have a reduction in voltage as I go across here. And then I put my voltmeter across the light bulb itself. I would get my lowest voltage, 9.997, let's say. So I would get a voltage gradient across here, but notice that...
So again, the voltage gradient, when you say that word, all you're really saying is a reduction in the pressure, because you've used the pressure. You did something that made it, you've broken the elasticity of the system somewhere, and you've created a deformation, okay, that isn't elastic, where you're not going to get the energy back. And that's what the light bulb is doing, essentially, is it's dissipating the pressure by moving a bunch of atoms in the filament and causing the filament to start falling apart and glow, okay, losing photons.
I have a lot of voltage to go across this light bulb. Now, if I could measure across the bulb itself and get smaller and smaller, I'd see less and less and less and less voltage until I got to where my two probes were at the same place. And that would...
You can sort of understand that any of the elastic movement out, the conductor moving out, is sort of lost energy. Because, that energy, how to say it, it's not going in the direction. You're not going to get it back in the positive direction. You're just going to keep getting it back in the wrong direction. Okay, so once you've got the energy going in the wrong direction, it's hard to get it back into the right direction. Not impossible. Clearly, water waves do it, right? I mean, water waves have a pressure that moves this way, and the fact is that the pressure can't get where it wants to go. It's too hard to push the mass, so it goes up and pushes the water up against gravity. And then gravity gives it back again. But if there's no gravity, you could sort of understand that water that went up wouldn't be coming back. It would just go that way, and you'd lose it forever. So without gravity, there's nothing to pull your water back. Now the protons, again, are elastic, and they're attractive force to the electrons, so they can pull things back.
Read 0 volts. So that voltage gradient only exists while there is current flowing. And this brings up another point, because I can already hear people saying, well, that means that the electrons are inconsequential. We don't need the electrons. Yes, we do.
Okay, and so this is where he just sort of says the standard stuff, which is, well, the electrons, when you move an electron, it makes a field. No, it makes a field all the time. And all you're saying is when I move the field, when I change the field, that's when I can make something happen. Just like the magnet doesn't do anything until I push it into something. All right, I can't make electricity with a magnet unless I constantly change its position. I have to move it, and all I'm doing, though, is moving the magnetic field. I'm changing the pressure in something by moving it.
The electrons establish the...
I'm creating more reflections, less reflections. I'm compressing reflections. I'm expanding reflections. When my hand moves away from you, I'm diluting the number of reflections you're getting. when I move it towards you, I'm increasing the number of reflections that get to you.
Electromagnetic fields. So even a tiny, tiny movement of the electrons establishes these fields, but the electrons must be moving for the fields to exist.
See, so that's just wrong. The electrons don't need to move for the field to exist. The field has to relax, has to increase pressure or decrease pressure to be adding or subtracting it. To make the pressure of the wire change, it has to create a change in the pressure of the external environment. And it can only do that by compressions and expansions.
So the electrons don't carry the energy is carried by the fields, but
Yes, and the fields are in the universe, okay? The empty space has all the energy in it. The material space is really just energy sinks. That's why there's gravity.
fields don't exist without the moving electrons.
So again, the fields always exist. The field always exists, and all you're really saying is it's critical that the field changes for there to be flow changes. Once I blow the balloon up, it's blown up. All right, I have to let the balloon lose its stuff before I can blow it up again.
And another thing that needs to be said is a lot of people are saying using lumped models is not telling the whole story. Well, it isn't, but it's telling the story from a macro view rather.
Yeah, I know, but again, it's really, you can do the model very crude or you can do the model very exact. And the point is that for physics subjects, the hope of most of the people interested in physics is that they're getting a model that's as close as possible to modeling the actual functions. And you know, a lot of these models that people are using, frankly, aren't very close to, in my opinion, to anything that could possibly be the actual. Glass beads isn't a very good analogy. Bent fabric isn't a good analogy.
Than a micro view. So, for example, when we look at a Zener diode,
Oh, I don't know if we need to do this part.
which I'm not going to explain right now, I'm just going to say something real quick. There is the symbol for a Zener diode. You can look at this as majority and minority charge carriers reacting to a p-n junction, or you can look at it as a little.
Okay, so this is a little bit too, there's no point. I mean, this is nowhere near any, but this just says that Zeners have thresholds, okay? They turn on at certain amounts and turn off at certain maximums. So they have ranges where they will only function in a certain way in this range, and then when they're in a different range, they function exactly the opposite, that kind of thing. They're switching diodes, you could argue. But anyway, so that's not really useful, I don't think. Let's go to the very end, see if there was any other point he had to make.
The lumped models are perfectly good. They are just a macro view rather than a micro view.
Okay, so again, no, it's like how far they are from accurate is the point. All right, so I think we all would hope that the models would be not too lumpy. Yeah, not too generalized, not too simplistic, because those metaphors end up just being dangerous to the truth. All right. I mean, that's why you're having this conversation, is because somebody's playing games with the concept, and so turning induction into a source of energy when, it's a symptom of energy. All right. I think that's all that I need to. I mean, there was a lot in here, so blah, blah, blah. Let's see if he can get anything out of it that's useful, or see if he's willing to discuss these particulars that sort of indicate that you need to view. There's a certain facts out there that sort of prove that, yes, this is just about electron pressure. Again, it's this money argument. When you give $10 away, you lose the $10. You don't need an opposite force to take the $10 from you. You already lost it by giving the $10 away. Well, the same kind of argument can be worked with what happens when you add electrons or subtract electrons. You automatically make the proton stronger if there's less electrons obscuring them, so to speak. So yes, something becomes positive, but it only becomes positive because you reduce the number of negatives. Okay, you took out the negatives. it's really just about increasing and decreasing the number of electrons, and that's all it's really about. So it's the color purple, and you're just saying the only color I can change are the blue things. I can't mess with the red things, so we'll call them the protons. So I can't change how much red there is, but I can change how much blue there is. And so I can make it look very red, or I can make it look very blue, all right, by adding blue. I can have purple. Nothing. We could argue. So I can tend to make a violet, or I can tend to make a purple. I can go to the blue range, or I can go to the red range. All right? But all I'm adding is blue, or subtracting blue. So electrons, you're just adding and subtracting electrons, and the symptom is that protons are more interesting when you take the electrons away. All right, something like that. That understanding, I think, is essential to proper modeling, accurate modeling. All right, anyway, enough of a video. So, till the next time, and such, and so forth, and whatnot. This has been draftphysics.com, debatephysics.com, but I can't find anybody willing to debate. So if you know anyone who is willing to talk and argue, okay, and not get insanely personal. I mean, you can call somebody an asshole or something, but you can't talk about their mother or their sisters or all of that crap, or you can't dox them. You can't do all this bullshit. Okay, you have to behave like something near a civilized human. You can't threaten to axe murder. Anyway, let me know if you know of anybody capable of being reasonably civil and defending physics. All right. Anyway, so till the next time and such. Yeah, that's a good enough ending. Till the next time, probably.